Bismillahirrahmanirrahim. Today in chapter 9, we will study about the emission and air pollution. Up till chapter 8, we have studied the exhaust flow, exhaust processes, and what all is happening after the exhaust. Now, after the exhaust, what these exhaust gases are doing to our atmosphere and to our system. Let's see the emissions and the air pollution. There are three major causes of these emissions. One is the non-stoichiometric combustion. Second is the dissociation of the nitrogens and impurities in the fuel air. So these are the three major reasons causing the emission in our atmosphere. Now these of concerns are these hydrocarbons, carbon monoxides, oxides of nitrogen, particulates, other emissions, aldehydes, sulfur, lead, and phosphorus. So these are we will study one by one. Now first, the hydrocarbons. Exhaust gases leaving the combustion chamber of an SI engine contains up to 6,000 parts per million. This is 6,000 parts per million of hydrocarbon components, the equivalent of 1 to 1.5 of the fuel. Just now see this yellow portion, just as percent means out of 100. So parts per million or parts per million means out of a million. Usually describes the concentration of something in water or soil. 1 ppm is equivalent to 1 milligram of something per liter of water, mg of oblique L, or 1 milligram of something per kilogram soil, mg per kilogram. So part per billion is like this. So exhaust gases leaving the combustion chamber of an SI engine contains up to 6,000 parts per million of hydrocarbon components, the equivalent of 1 to 1.5 of the fuel. About 40% of this unburned gasoline fuel components. So there is 40% of this unburned gasoline fuel components are there. The other 60% consist of partially reacted components that were not present in the original fuel. So small non-equilibrium molecules form with large fuel molecules break up. Thermal cracking during the combustion chamber. As we know that fuel consists of different molecular structures, smaller molecules, larger molecules. So when the larger molecules break up by thermal cracking process, so we get this small non-equilibrium molecules are formed. It is convenient to treat these molecules as if these contains one carbon atom. Now they contain at least one carbon atom. So the makeup of hydrocarbon emission will be different for each gasoline blend depending upon. So each gasoline fuel is having different combination of hydrogen and carbon. The structure is different. So molecule structure is different. So the emission will be different depending on the original fuel components. The original fuel components means hydrocarbons, they are in different shapes. Combustion chamber of the geometry, very important. If the combustion chamber of the geometry, how it is like this piston head is of what shape, this piston block from the top in the center is of which shape. So all these things depends. Then the engine operating characteristics or parameters, whether engine is operating at wide open throttle or part open throttle or with supercharger or with turbocharger. So all these leads to different types of hydrocarbon emission. Now, the causes of hydrocarbon emissions, these are the reasons due to which we receive hydrocarbon emission. Non-stoichiometric air-fuel ratio, if the air and fuel is not in stoichiometric ratio, due to which we get this emission. If we have incomplete combustion, means the piston engine is moving very fast and there is less time of combustion or very slow, then we have different type of combustion properties, so there will be emission. Crevices volume, the gaps between the piston and the wall and in the spaces in the head creates a crevice volume, and that is also one of the factor of causes this hydrocarbon emission. Then leak past exhaust valve. leak past at the end of the exhaust gases, there's still the temperature, or during the exhaust gases, the temperature and pressure is quite high. And some of the gases might leak past the exhaust valve, so they will add in the hydrocarbon emissions. Wall overlap timings means both the inlet and the exhaust valves are open for 15 to 50 degrees Celsius degree of the crankshaft rotation. So at that overlapping time, we have some flow going into the exhaust and some flow going into the inlet. So that the overlapping is also uh, one of the factor of causing this hydrocarbon emission. Then deposits on combustion wall chamber. So few molecules of fuels are deposited on the combustion wall chamber, or the oil layer is to oil on the combustion chamber wall. So combination of both these will also affects the combustion property in the combustion cycle. So this will also leads to the hydrocarbon emission in the end. Then two-stroke cycle engine, because of their peculiar design, they will have some hydrocarbon emission in the exhaust. And CI engines, because they operate in lean regions, so they have different combustion properties. So there is also some hydrocarbon emissions. So these are the few reasons for the causes for the hydrocarbon emission. Now, emission from an SI engine as a function of equivalence ratio. Let's see the example diagram here. On our x-axis, we have this equivalence ratio phi. Phi is 1 when we have an ideal standard stoichiometric ratio. Air fuel mixture is in desired range. On our left, we have a lean region. Here, lean region means we have more of oxygen, less of a fuel. And on our right, we have a rich region in which we have less of oxygen, more of a fuel. And on y-axis, we have amount of emission in exhaust flow. So let's see this. This is your hydrocarbon emission, high during the start, then going down. As the equivalence ratio is changing, temperature is changing, they are going high in rich region. Now, at the start, due to lean, the NOx very less. When phi is equal to 9.95, we have a maximum temperature and maximum pressure. At maximum temperature, we have the maximum NOx elements. So here we have the maximum NOx before this equivalence ratio of 1. So more in them, it will going to decrease like this. Then if carbon monoxide, initially we have a rich oxygen, so no problem with the carbon dioxide forming. But when we have a rich mixture with less of oxygen, we have a more of carbon monoxide. Now let's see. A rich air fuel ratio does not have enough oxygen to react with all the carbon and hydrogen, and both hydrocarbon and carbon monoxide increases. So less of oxygen, both hydrocarbon emission and carbon monoxide increases. Hydrocarbon emission also increases at very lean mixture due to poor combustion and misfire. At this region, it is also high due to very lean mixture and poor combustion and misfires. The generation of NOx, nitrogen oxide emission, is a function of a combustion temperature, as we know, being greatest near the stoichiometric condition when temperature are the highest. At stoichiometric condition, the temperature is very high. So at somewhere here, 0.95, when equivalence ratio is this, we get the maximum temperature, so we get maximum NOx. Peak NOx emission occurs at slightly lean condition when the combustion temperature is high and there is an excess of oxygen to react with the nitrogen. Now, the second part of the causes, high carbon monoxide. Okay. Now, carbon monoxide generates with rich fuel mixture when there is not enough oxygen to convert to carbon dioxide, and some fuel does not burn out and convert to carbon monoxide. Now, when we have a less of oxygen, at the end result will be in carbon monoxide. If we have abundant of oxygen, then there will be no carbon monoxide, simple. But rich air fuel mixture, less of oxygen, and result in carbon monoxide. Typical exhausts of SI engine consist of 0.2 to 5% of the carbon monoxide, which is not only considered as undesirable, but considered as lost chemical energy. So this typical SI engine It consists of 0.2 to 5% of carbon monoxide, which is undesirable and but considered as loss of chemical energy. So carbon monoxide plus half mole of oxygen give us carbon dioxide plus heat. So most of the carbon monoxide will be developed when engine running rich, like at startup and accelerating under load. A well-designed SI engine operating under ideal condition can have an exhaust mole fraction of carbon monoxide as low as 10 raised to power minus 3. CI engines that operates overall lean generally have very low carbon monoxide emission. So this is one plus point of the CI engine. Now NOx. Let's see the third point cause of this hydrocarbon emission is oxides of NOx. Now, exhaust gases of an engine can have up to 2000 parts per million of oxides of nitrogen. Most of this will be nitrogen oxide with a small amount of nitrogen dioxide and traces of other nitrogen oxygen combination. So variety of nitrogen oxygen combination will be there. Majority of this will be nitrogen oxide and nitrogen dioxide and other NOx. These are generally grouped as together as NOx or NOx, with X representing some suitable number. Now, generation of NOx in an engine as a function of combustion time. Many modern engines produce lower NOx emission due to fast burn combustion chamber design. So due to the combustion chamber design, that fast burn combustion design, NOx emissions is there. On our x-axis, we have this time frame. On our y-axis, we have concentration of NOx. As we know, when we have a maximum temperature, when phi is equal to 0.95, we have the maximum NOx. So when the equivalence ratio is 1, we have less of NOx, and the equivalence ratio is more lean. So 0.770, we have again these very less of a NOx. Now, NOx is a very undesirable emission, and regulation that restricts the allowable amount continue to become more stringent. So released NOx reacts in the atmosphere to form ozone, and it's one of the major causes of the photochemical smoke, which mostly happens in the cold weather conditions. The release of NOx reacts in the atmosphere to form ozone and is one of the major causes of the photochemical smoke. NOx is created mostly from nitrogen in the air. Nitrogen can also be found in fuel blends. Oxides of nitrogen, there are a number of possible reactions that forms nitrogen oxides, all of which are probably occurring during the combustion process and immediately after. These includes but are not limited to this. So variety of nitrogen and oxygen combination, and we are getting different end products. So the generation of NOx in an SI engine as a function of spark timing. Generation of NOx in an SI engine as a function of spark timing. So we on x-axis we have spark timing degrees before TDC. So this is 50 degree before TDC, 40 degree, 30 degree, 20 and 10 and so on. And this is the mole fraction of NOx in exhaust percentage, 0.1, 0.2 and 0.3. When we have a phi is 0.95, we have a higher NOx, and when we have phi 1 ratio 1 equals ratio 1, then we have a less NOx. Now the photochemical smoke. NOx is one of the primary causes of the photochemical smoke. NOx is one of the primary causes of the photochemical smoke, which has become a major problem in many large cities of the world. So NOx is one of the primary causes of photochemical smoke, which has become a major problem in many large cities of the world nowadays, because smoke is formed by a photochemical reaction of the automobile exhaust and atmospheric air in the presence of sunlight. So the formation of smoke is formed by the photochemical reaction of the automobile exhaust and atmospheric air in the presence of sunlight. Nitrogen dioxide decomposes into nitrogen oxide and monatomic oxygen. So nitrogen dioxide plus energy from sunlight we get nitrogen oxide plus monatomic oxygen plus smoke, and this monatomic oxygen is highly reactive and initiates a number of different reactions, one of which is formation of ozone. So monatomic oxygen is highly reactive and initiate a number of different reactions, one of which is formation of ozone. Of monatomic oxygen plus diatomic oxygen give us O3. Now the next part is particulates. Particulates, causes of emission. The exhaust of CI engine contains solid carbon soot. Now the exhaust of CI engines contains solid carbon soot, particles that are generated in the fuel-rich zone within the cylinder during combustion. These are seen as exhaust smoke and are undesirable, odorless, and pollution. So we have already studied while we were studying chapter 7, the combustion. The in CA engines, it is mostly the solid carbon soot are the also end product in the exhaust of the combustion. Maximum density of the particulates emission occurs when the engine is at load at wide open throttle. So at wide open throttle condition, we have maximum density of particulate emission. At this condition, the maximum fuel is injected to supply maximum power because we are getting maximum amount of air, so resulting in a rich mixture and poor fuel economy. Soot particles are cluster of solid carbon sphere. So soot particles are cluster of solid carbon spheres. These spheres have diameters from 10 nanometers to 80 nanometers, and 1 nanometer is equal to 10 raised power minus 9 meters, with most within the range of 15 to 30 nanometers. So this is the maximum range, and mostly they are in 15 to 30 nanometers. The spheres are solid carbon with hydrocarbons and traces of other components. These spheres are solid carbons with hydrocarbons and traces of other components absorbed on the surface. A single soot particle will contain up to 4,000 carbon spheres. So this sphere of solid carbon soot having a hydrocarbon plus solid carbon and few traces of other components which are absorbed on the surfaces. A single soot particle will contain up to 4,000 carbon spheres. So these have 4,000 of carbon spheres. Now the next is the aldehydes, other emissions in which we have aldehydes, sulfur, lead, and phosphorus. Now, other emissions includes aldehydes when we are a major emission problem when alcohol fuel is used, and eye and respiratory irritants. So when we are using alcohol as a fuel in different forms, with the end products will be an eye and respiratory irritants. So emission will having these problems. When sulfur is in the emission, many fuel used in CI engines contain small amount of sulfur, which when exhausted contributes to an acid rain problem. We will study this thing in same chapter in second part. So many fuels used in CI engines contain small amount of sulfur, which when exhausted contribute to the acid rain problem. Unleaded gasoline generally contains 150 to 600 part per million sulfur by weight, whereas diesel fuel contains up to 5,000 parts per million. So if we are using unleaded gasoline, it contains 150 to 600 parts per million sulfur by weight, whereas diesel fuel contains up to 5,000 parts per million, so huge amount. Now, if emission, we have a lead problem here. Major additive to raise the octane number of a gasoline, as we know, tetraethyl lead is used to increase the octane number of fuel in gasoline. Alternate octane risers have to be developed as lead was phased out, being very poisonous pollutant. Previously, we were using lead in the gasoline to increase the octane number, now due to its harmful effect to the environment and to the human beings, so it is being phased out. First, low leaded gasoline was introduced, and then years later, no lead gasoline is used. So always use fuel with no lead. Okay, phosphorus. Small amount of phosphorus is emitted in Indian exhaust. These comes from impurities in the air, which we have. The air is coming inside the combustion chamber. It is after the filtration, but still there are some impurities. So some traces of phosphorus will be there, and small amount found in some fuel blend. So some few traces are found in the fuel blends and lubricating oil. So some traces are in air, in your fuel, in your lubricating oil, and in the exhaust will contain some phosphorus, and this is also dangerous. Now, the after treatments. Now we are getting these exhaust emissions in which we have hydrocarbons, we have carbon monoxide, we have NOx, we have other emissions, particulates, and all these. Now, how to treat them? There are three different methods to treat them. One is the thermal converter, one is the catalytic converter, and one is the exhaust gas recycle. So these are the three ways to do the after treatment of the exhaust emissions. In first, the thermal converters, secondary reaction occurs when such readily and completely if the temperature is high. So some engines are equipped with thermal converter as a means of lowering emission. So thermal converters are high temperature chambers through which the exhaust gases flow. So thermal converters are high temperature chambers through which the exhaust gases flow. They promote oxidation of the carbon monoxide and hydrocarbons which remain in the exhaust. So the thermal converter oxidize the carbon monoxide and hydrocarbons which remain in the exhaust. Now the second form is the catalytic converter or the after treatment. The most effective after treatment system for reducing engine emission is the catalytic converter found on most automobiles and other modern engines of modern or medium or larger size. And presently in latest vehicles, all the vehicles are equipped with this catalytic converter. Hydrocarbons and carbon monoxide can be oxidized to H2O and CO2 in the exhaust system and thermal converters if the temperature is held at 600 to 700 degrees Celsius. So if the temperature is held from 600 to 700 degrees Celsius in the exhaust thermal converter, we can oxidize the hydrocarbons and carbon monoxide to carbon dioxide and H2O. If certain catalysts are present, if we are using some certain catalyst, the temperature needed to sustain this oxidation process is reduced to 250 to 300 degrees Celsius. So we are using some catalyst, and due to the help of that catalyst, we are reducing the temperature for this oxidation process to 250 to 300 degrees Celsius as compared to 600 to 700 degrees Celsius, making for a much more attractive system. A catalyst is a substance that accelerates a chemical reaction, as we know from our chemistry knowledge, by lowering the energy needed for it to proceed. A catalyst is not consumed in the reaction, so function indefinitely unless degraded by heat, age, contamination, or other factor. So the catalyst is not consumed in the reaction and so functions indefinitely unless we have these three factors: degraded by heat, age, contamination, or other factors. Catalytic converters are chambers mounted in the flow system through which the exhaust gases flow. So catalytic converters are chambers mounted in the flow system through which the exhaust gases flow. So the catalytic converters are basically like thermal converter. They are like some chambers mounted in this system. These chambers contains catalytic materials which promotes the oxidation of the emission contained in the exhaust flow. Let's see. Generally, catalytic converters are called three-way converters because they promote the reduction of carbon monoxide, hydrocarbons, and NOx. So generally, they are three-way converters because they promote the reduction of carbon monoxide, hydrocarbons, and NOx. Most consist of a stainless container. So the overall body is made of stainless steel container mounted somewhere along the exhaust pipe. of the engine mounted somewhere along the exhaust pipe of the engine. Inside the container is a porous ceramic structure. Inside the container is a porous ceramic structure through which the gas flow. So inside that steel container, there is a porous structure, ceramic structure through which the gases flow. In most converter, the ceramic structure is of single honeycomb structure. In most converter, the ceramics is single honeycomb structure with many flow passages. Some converter use loose granules ceramics with the gas passing between the packed sphere. So instead of the ceramic single honeycomb structures, some converter uses loose granule ceramics with the gas passing between the packed spheres. Volume of the ceramic structure of the converter is generally about the half the displacement volume of the engine. So this is very important. The volume of the ceramic structure of a converter, ceramic structure, not the whole. So the volume of the ceramic structure of converter is generally about the half the displacement volume of the engine. This results in volumetric flow rate of the exhaust gas and such that there will be 5 to 30 changeovers of the gas each second through the converter. So if we are using 3 liters of volume, total volume of engine is 3 liter. So the ceramic structure volume should be 1.5 liter. The result in the volumetric flow rate of the exhaust gases through such that there are 5 to 30 changeovers of gases each second through the converter. Now, the catalytic converters for CI engines needed larger flow passages because of the solid soot in the exhaust gases. So, another problem for the CI engine, we need a larger flow passages because of the solid particle soot in the exhaust gases. The surface of the ceramic passages contains small embedded particles of catalytic material that promotes the oxidation reaction in the exhaust gases at its passes. The aluminum oxide, alumina is the basic ceramic material used for the most catalytic converter. So the aluminum oxide or alumina is the base ceramic material used for the most catalytic converters. Alumina can withstand high temperature. So properties of this alumina, which is using as a base ceramic material, are that it can withstand high temperature. Number one, it remains chemically neutral. Number two, it remains chemically neutral. It has very low thermal expansion. Number three, it has very low thermal expansion. So thermal conductivity is very less. And it does not thermally degrade with the age. So it does not thermally degrade with the age. So there are 4 factors due to which the alumina is used as the base ceramic material. That is high temperature, remains chemically neutral, very low thermal expansion, and it does not thermally degrade and with the age. The catalyst materials most commonly used are platinum, palladium, and rhodium. So the catalyst materials which are most commonly used are platinum, palladium, and rhodium. So there is a difference. The base ceramic structure material is aluminum oxide, and the catalyst material is platinum, palladium, and rhodium. Don't get confused in this thing. Okay. Now the palladium and platinum promotes the oxidation of carbon monoxide and hydrocarbon as mentioned here. Palladium and platinum promotes the oxidation of carbon monoxide and hydrocarbon, whereas the rhodium promotes reaction of NOx in one or more of the following way as mentioned here. So the rhodium promotes reaction of NOx in one or more of the following way. So with this is the just for your knowledge, with this very good animation of the how the catalytic converter works, you can see from your YouTube channels different very interesting videos. So with this, we come to the end of our today's part 1 lecture. I hope you are enjoying my lecture, and please kindly subscribe and